Welcome to module D, lecture 2. In this lecture, we shall discuss about various methods for trip distribution and then two specific approaches or methods which are used under growth factor techniques, that is uniform growth factor method and average growth factor method. Those two techniques also we shall discuss. In our first lecture on trip distribution, we talked about why and what we do in the trip distribution process, what are the inputs to this process, what are the outputs from the trip distribution stage, and then specific two types of matrices which we handle in the trip distribution context. One is the production attraction matrix, one is the origin destination matrix. How these are different? To remind you again, the PA matrix is not directional, the total production and attraction, that is what we are saying zone wise. Okay. So, how many productions are happening in zone 1 and which are with respect to travel from 1 and 2, between 1 and 2. But the OD matrix, we give specific directional travel. If we say 1 to 2, that means specifically it is from 1 and to 2, that is direction towards zone 2. That is basically fundamentally difference between this PA matrix and OD matrix, and we also explained how we can convert PA matrix to OD matrix if we know the necessary inputs, right. With this background, today let us discuss about various methods of trip distribution. In this slide, you can see so many methods or so many models which are mentioned here. Actually, all the works or all the models or methods can be classified into two broad groups. One, we can call it as growth factor models, and then other categories of model could be called as synthetic model. Growth factor models are simpler, may be used very effectively to update short term update of the matrix, okay, trip distribution matrix which are already there for short update when there is no significant change in the transportation network. And synthetic models are more rigorous, okay, more logical, reasons are inbuilt inside, right, and they can be used even to estimate the individual cells. Now, there are again within that there are gravity models, there are opportunity models, there are linear programming approach, so many things can be used and all can come under synthetic model. In fact, if you talk about gravity model is not just one model. There are so many again models have been developed by researchers over several decades, which all may be called as gravity model. So, again it is a category of model. Again opportunity model, we can consider it as a category of model. Within that we have intervening opportunity, we have competing opportunity and so on. So, in this module trip distribution, we shall discuss about all of these models. So, to start with, we shall take up the growth factor models first, and then we shall go to synthetic models. So, first let us take it the growth factor based method. In growth factor method, what is fundamentally done is as follows. The present travel patterns are projected to the horizon year, that is the future. So, we know the present travel, present everything is known, that is the fundamental assumption in growth factor models. Then by using growth factors, we try to get the projected value in the future or in the horizon year or in the design year, whatever you say. So, Tij, if I say that future value, how many travel will happen from zone I to zone j, directional travel, maybe we will say that Tij, capital Tij equal to small Tij. Small Tij indicates how many observed base year trips from zone I to zone j, multiplied by a factor which is called E. E is the growth factor. Okay. Now, this growth factor, we have again said that there are several models which are all put under growth factor methods. How they are different from each other? They are different in terms of how we are calculating that E or how we are applying that E, growth factor. There one model growth factor based method or model is different from another growth factor based model. But every case, the small Tij, that is the present or the base year element, Tij element is known to us, and we are applying a factor which is called maybe growth factor to that to get our future value of that cell, that is capital Tij. So, capital T represent future value, small Tij represent the present value, and the present value is multiplied by growth factor E. Now, all these growth factor methods are used in urban planning for short term update. We shall discuss more about the applicability. Each approach, the growth factor methods have their own advantages as well as they have own limitations. Synthetic models have their own advantages, but not that always we would like to use synthetic models. There are so many cases where you cannot use synthetic models or where you need not use synthetic model. You can use simply a growth factor based model to do your work. That is what is specifically mentioned here in the last point. They are used in urban planning, particularly useful for short term update. Now, there are several methods or several models which have been developed. All may be called growth factor based method, because the fundamental is same. You have the small Tij known in the base year or the current year, and we want to find out capital Tij value for the horizon or design year using the knowledge of small Tij, that is the current value, and by multiplying that with the growth factor. Okay. So, fundamentally all growth factor models are same. In uniform growth factor method, a single growth factor E for all the elements in that matrix, we use only one value of E, and that one value is applied to each cell of the matrix to update small Tij to capital Tij. So, the E value is same for all the cells. That is why it is called uniform growth factor. That every cell we are using or multiplying with the same growth factor value. So, that is called is as uniform growth factor method. Let us take an example to understand it. Let us say the present OD matrix is given like 1 to 1 60, 1 to 2 150, 1 to 3 200, 1 to 4 150 and like that. So, each cell. Now, these cell values are what? These cell values are small Tij, small Tij. Okay? And we are saying that the future trips generated from zone 1, 2, 3, 4 are this matrix, in the whole matrix you can see that Tij equal to Tji. Okay. So, the productions and attractions for each zones can be obtained, and for each zone the production and attraction, for a zone the production and attraction will be same, because Tij equal to Tji. Okay. So, the present one we can get, what is the production for zone 1? 60 plus 150 plus 200 plus 150. What is the attraction for zone 2? Let us say 150 plus 20 plus 300 plus 300. So, like that the present productions and present attraction from for 1, 2, 3, 4, these 4 zones are known. What is also given? The future generated trips in zone 1, 2, 3, 4 are 940, 1570, 1420 and 1530. Now, obviously, attractions, taking that production attractions for one particular, for any zone, the production attraction is same here in this example. So, the attractions also are likely to be this same 940, 1570, 1420 and 1560. Now, we would like to get these future trips using the uniform growth factor method. How to do that? So, the same matrix is shown here, you can see 1, 2, 3, 4, 4 zones at the origin end, 4 zone in the destination end. What we have done? We have calculated the total present productions, and attractions are not shown, but they will again be same. So, the present productions are 560, 770, 680 and 600. And we know then total how many trips are happening in the whole study area consisting of 4 zones, 560 plus 770 plus 680 plus 600. So, we have 2610 trips, 2610 trips are happening now. The future productions are also given in this example. So, go back to the previous one, you can see 940, 1570, 1420 and 1560. So, those values are put here. So, we know that the future total trips in the study area will be addition of all these numbers. So, which comes out to be 5490. Okay. So, the present total trips 2610, future total trips 5490. So, what will be my growth factor? My growth factor will be simply 5490 divided by 2610. So, 2.103. So, this is my growth factor, and then this is, since this is uniform factor method, what we will do? We will multiply each cell by this growth factor of 2.103. Okay. Then as per this model, we will get the future values. Exactly that is done. Exactly that is done. You will see the values are calculated, and obviously, say for zone 1, if you see interestingly, now the total number of trips will match 5490, that is what our target, and what we predicted also is 5490, because the growth factor total trips are upgraded. So, the total trips will match, but then look at each zone, what you are getting, it is not very encouraging. Okay. We were expected to get, supposed to get, our targets were to get 940 for zone 1, we got 1178. For similarly for zone 4, our target was 1560, we got 1262, and the remaining also some differences. Okay. And as I said here, in this case Tij and Tji are same. So, for take a zone, you will find the productions and attractions are same. For zone 1, 1178 production, 1178 attraction, zone 2, 1620 productions, 1620 attractions. This is because Tij equal to Tji. both elements are same. So, what we find from this, that we are able to upgrade the total trips as per our requirements. So, we somehow get a matrix where the total number of trips are matching, or to the total number of trips is matching. But if we say origin and destination wise, or zone wise, rather zone wise, if we see, we find that what we should actually get and what we got by applying uniform factor method, the difference is very significant. Okay? There is a gross kind of mismatch. Okay? So, this need to be improved further. So, as we said, what are our disadvantages? You can say that the assumption of a single growth rate for the entire study is not probably correct. It cannot be correct, because different zones are there and they have all unique rate of growth. If you see the present trip production is 560 for zone 1 and the future is 940. So, what is the growth? We can calculate it, 940 divided by 560. Similarly, growth zone 2, we can see the growth 1570 by 770, zone 3 1420 by 680 and zone 4 1560 divided by 600. So, you will clearly see that the growths are not same in all zones. It cannot happen. Different zones in an urban area, the growth in terms of productions, in terms of attractions, okay, across different zones, the growths cannot be same. But what we assumed here, one growth factor for every cell, all cells, one growth factor. So, what happened? My total number of trips matched, but row wise the production attractions did not give good match, because we did not recognize that each zone has its own growth. Second, it underestimates and overestimates movements where present day development is limited and intensive respectively, because you are using a multiplier. Of course, this is a common issue probably with all the growth factor based model. Since you are using and in this case the same multiplier, then the lower values will remain lower, the higher value remain higher. Because if a zone is producing very low, then on that number we are using a multiplier. So, obviously, the future also will still be less, and here uniform growth factor. So, all the cells are getting multiplied by say whatever was the value 2.1. So, every cell gets multiplied by 2.1. So, low values also gets multiplied by 2.1, high value gets multiplied by 2.1. So, low will remain low, high will remain high. And if third point, if any of this cell is 0, then whatever you get is also 0 in the future, because you are multiplying 0 with something. So, always it will be 0. This is particularly is a common problem for all the growth factor based method. Okay. Now, to overcome this, then next came a different model or a method, what is called as average growth factor method. So, what was the issue? The issue was earlier uniform factor method, that we did not consider the growth of different zones, we did not recognize that. Every cell we multiplied by the same growth factor. So, obviously, my error was more. Here what we are doing? We are calculating separate growth factor for separate or cells. Each cell is separate growth factor. Why is cell separate growth factor? Now, the cell is Tij. So, I have got two tags, one is I, another is J. So, any cell belongs to or is a part of a column which is J, belongs to a part of a row which is I, from zone to zone. So, there are two tags I, J, and trip is happening between I and J. So, what it did, it does, it takes the average growth of I and J. So, you can see here the capital Tij, future Tij value, that is future or design year or horizon year Tij value is small Tij, what is happening now, multiplied by Ei plus Ej. Ei is the growth of zone I, Ej growth of zone J by 2. That means, we are taking the average of that. So, every cell it has got two ends, one is I, another is J. So, whatever is happening in I, whatever is happening in J, both growths we consider and take the average of that, and so this cell growth will happen as per that growth. So, every cell Ij combinations will be different. So, the growth factor also will be different. Fantastic. So, that way it is better and much more logical than the uniform growth factor method. So, that is we have said here what is Ei, capital Pi by small pi, that means productions, expected productions in zone I, future row total, and the present row total is small pi. Similarly, growth of zone J, Aj, attraction of zone J in the future divided by the present attraction of zone J, that is small Aj. And what I said that Pi is the future generated trips in zone I, small pi present generated trip in zone I, Aj future attracted trips in zone J, Aj present attracted trips in zone J, and capital Tij is the future trips from I to J, small Tij is the present trips from I to J. Okay. Now, once you complete one distribution, you will still find that the projected and actual trip ends may not match, in fact, will not match. Then what is that we have to do? We can go for one more iteration. Whatever will be your new matrix after first iteration, you assume that that is your input matrix and repeat exactly the same procedure what you adopted initially. Go for one more iteration. So, like that iteratively if you do, you will find the target and actual estimated productions and attractions in the future will match very closely. And if they match closely, then you know that your internal cell distributions are probably reasonable, because they give close match to your target row total and target column total. Let us take an example here. 100, 400, 200, those are the cells 1 to 1, 1 to 2, 1 to 3. Here is also Tij equal to Tj1, because you see 1 to 2 400, 2 to 1 is also 400, 1 to 3 is 200, 3 to 1 is also 200. So, here also the productions and attractions for a zone are same. Now, the future trips generated from zone 1 to 3 are known to be 925, 850 and 1050, and we want to distribute the trips, get the cells This 9 values we want to get in the future, which will give us a better match of the row totals and the column totals with respect to zone 1, 2, 3. That is what is our target using the average growth factor method. So, we do it here, we start. What we do? We find out the growth factor of zone I, it is 1.32, zone 2 1.21, zone 3 2.33. How we got this one? We took the future of productions of zone 1 925 divided by 700, then we get 1.32. Similarly, you will get for attraction end also, because for each zone production and attraction values are same. So, here also it is column total, if you see present is 700, our target is 925. So, I get a growth factor of 1.32. Like that, each growth cell, each zone you can get the growth factor. So, we got 3 growth factors for the productions of ends, 3 growth factor the attraction ends. Of course, they are similar here. For each zone, the growth for the origin and growth at the destination for productions and attractions are same. Now, what we will do? We know say T 11 means one end also is 1, the other end is also 1. So, origin end the growth is 1.32, destination end 1.32. So, 1.32. So, 1.32 plus 1.32 by 2 into 100, 100 was the original value. So, they remain 100 into 1.32. So, you get total value of 132. Similarly, T 12 growth of zone 2 is 1.21, 1 is 1.32. So, average of 1.32 and 1.21 into 400. So, you are getting 507. So, like that you take each cell, see what is I, what is j, what is the growth at the production end of I, what is the growth at the attraction end of j, take the average growth, multiply that cell respective cell with that growth to get the future values. So, like that we got it. So, what we can say here the total target trips in the future is matching as usual. This match we also got in the uniform factor method. This is not a surprise, that this is not something better what we got here. Anyhow, there also we got it uniform factor method, but look at this value. We got 1005, whereas our target was 925. Zone 2 we got 927, whereas we wanted to get 850. Zone 3 we got 893, whereas we wanted to get 1015. So, still there is a mismatch, and in uniform growth factor method we could not do anything else, we had to leave it. Here we can still try to make it better, right. So, we have to go for the next iteration. So, what we will do? We will say, as you started with a iteration with an initial matrix and then you had target total and the growth factor at the origin end and the destination end, and then you updated it. Now, assume that this is your starting matrix. That means, your 1005, 927, 893 and the internal cells whatever you get is this whole thing is your starting point, and you want to modify this cell so that for zone 1 you get total production as 925. So, with a growth factor of 0.92. Second case, instead of 927 you want to get 850. So, with a growth factor of 0.92. Third case, you got 893, you want to get 1050. So, with a growth factor of 1.18. So, these are your new growth factor for the next iteration. As you got growth factor here 1.32, 1.21 and 2.33. Instead of that, now you got your growth factor as 0.92, 0.92 and 1.18. Okay. So, you will go to a second iteration, and as you go to the second iteration, you get again a matrix. Just see what is your E values, growth factor values. Now, obviously, you can decide your acceptable error limit, that okay, I do not need to be, I do not expect this to be exactly 1, but maybe 0.99 is okay for me. Someone else may say okay, 0.95 or 96 to 1.04 is fine for me. Okay. Somebody may say as well 0.99 to 1.01, okay, you set your limit, but then you need more number of iterations, right, and you will see that all these cell values will get adjusted slowly in such a manner that your target total and what you will get from your updated matrix for each zone will match more closely. So, obviously, now what you got as 0.92, 0.92 and 1.18. If you go to the next iteration, you find each of these values will move maybe closer to 1. They may not be exactly 1, but as you go for more and more iteration, it will move towards 1 value, and then depending on what is acceptable for you, decide an error limit. Every planning estimates will have some error. So, if you 5% error is okay or 10% error is okay, you decide whatever is your acceptable error limit. Accordingly, you decide, and that many iterations probably will be required, or more and more iterations will be required to get the results as per your expectation. So, what are the disadvantage? Disadvantage here is again multiplying factor has no real significance. Of course, we duly considered more logical factor we use, because earlier just one factor for every zone, whereas we know that each zone has different growth, right. And you talk about a cell, then I and j both ends are important. Okay. So, growth at I and growth at j both will influence, right. So, that consideration is there, but there is no real significance, it is just a factor, that is what we used it. What is the physical meaning of that? There is probably not much, nothing much can be said. There is no explanation of the movement between zones and the factors causing movement. We know that how many trips will happen will depend on actually the properties of the transport network, travel time, travel cost, connectivity, all these are very, very important. So, we do not consider any of those, simply some number game, we are doing some balancing, some factoring, so that we get our row total and column total, whatever we are getting from the modified matrix are matching closely with our target total. So, nothing beyond. Sometimes you may require a large number of iterations if you are depending on your error margin, and also the same problem is here. If any cell initially is 0, whatever you do finally end of the day you will get again 0, because you are multiplying a factor on that original value. So, if the original value is 0, everything is 0. So, to summarize, we discussed in this lecture about two broad methods of trip distribution, growth factor based method and synthetic method. We did not discuss in details, but we just mentioned that there are two broad categories or two broad approaches for modeling. Then we discussed what is really we do growth factor based method. Present cell we take, multiply it by a factor E or a growth factor, right, to get the future cell or in the horizon year or in the design year. Different methods varies, or different methods actually calculate this and apply this growth factor in different manners. That is why they are different methods, but all actually apply a factor to a given or the present cell to get the future or the design year or the horizon year cell. And then we discuss two specific methods, uniform growth factor method and average growth factor method, and explained you how they are applied with some example. So, with this I close this lecture. Thank you so much.